All right, let's talk about something that's absolutely critical in any lab or classroom: chemical storage. And it's so much more than just finding a spot on a shelf. When you do it right, you've got a system that keeps everyone safe. But when it goes wrong, well, it can be a real disaster waiting to happen. So let's get right into it. So I want you to just take a second and really think about this. Your lab, your classroom, your stockroom, what's really going on behind those cabinet doors? Are you 100% sure everything in there is playing nice? Let's take a closer look. Okay, so before we jump into all the rules and the how-tos, we really need to understand the stakes. I mean, we've got to see what happens when chemical storage goes totally wrong. This is the why behind every single rule we're about to cover. Okay, take a look at this. What's so wild about this picture is just how common this mistake is. We've got flammable liquids, in this case ethyl alcohol, just sitting out in the open, right on top of a cabinet that's specifically for corrosive acids. I mean, that's two completely different hazard classes right next to each other. It's a totally unnecessary risk. At first glance, this just looks like a shelf from any old cleaning closet, right? Well, think again. You've got bleach, which is an oxidizer. You've got vinegar, an acid, and ammonia, a base. Putting them all together like this is basically a recipe for a really dangerous chemical reaction. You mix bleach with ammonia, you get toxic chloramine gas. You mix bleach with acid, you get toxic chlorine gas. So yeah, this seemingly innocent-looking shelf, it's actually a serious health hazard. And here we have a silent threat. This bottle expired way back in 2008. You see, chemicals are not like a fine wine. They do not get better with age. Over time, they can degrade, they can lose their potency, or even worse, they can become unstable and super unpredictable. An old chemical is basically an unknown variable, and that's something you just don't want in your lab. Okay, so we've seen the chaos. Now let's talk about how to build some control. And look, you don't have to be a master chemist to get this right. You just need to understand a few core principles. Once you get the why, I promise the how becomes almost second nature. All right, if there's one term you take away from this today, it's this one: incompatible chemicals. This is the absolute heart of safe storage. The entire goal here is to figure out which chemicals are going to react dangerously with each other and then just put some physical distance between them. It's really that simple. So that one big idea breaks down into these three core principles. First, and this is a big one, don't sort your chemicals alphabetically. Sort them by their hazard category. So flammables go with other flammables, acids with acids, and so on. Second, you have to actively separate those incompatible categories. And third, just take a minute to understand the basic hazards of what you're working with. That knowledge, that's your best tool for staying safe. Okay, knowing the principles is one thing, but how do you actually apply them in the real world? Well, let's look at a system that's designed to do all the hard work for you: the Flynn Scientific Storage Pattern. Now, before you see a chart and your eyes glaze over, remember this: the key is not memorization. You don't have to memorize where every single chemical goes. You just need to get the logic of the categories. It's all about putting things in the right family. So let's start with the inorganic chemicals and see how this works. You can see right away that chemicals are grouped by their properties. You've got metals and hydrides in one group, sulfates and sulfites in another. But look at the big one over on the right, the acids. They are so reactive that they get their very own dedicated corrosion-proof cabinet. They need to be completely isolated from everything else. And it's the exact same logic for organic chemicals. They're all sorted into families, like alcohols, hydrocarbons, and organic acids. And again, the really special hazards get special treatment. Flammables are all kept together in their own fire-resistant cabinet, and any severe poisons, well, they should be stored securely in a locked cabinet. The whole system scales the protection to match the risk. So what does this actually look like in practice? Let's see the transformation from that chaos we saw earlier to a nice, calm, organized system. This before and after shot just says it all, doesn't it? On the left, you've got pure chaos, mixed hazards, unlabeled stuff, basically an accident just waiting to happen. And on the right, total control. Chemicals are separated by hazard into labeled bins. It's clean, it's clear, and most importantly, it's safe. Proper storage can also get really specific, and this is a great example. Take a look at these alkaline metals, things like sodium and potassium. These things react violently with water. I'm talking even just the moisture in the air. So the rule is you have to store them submerged under mineral oil. That oil keeps the water out and prevents a super dangerous reaction. It's the perfect example of knowing your hazard and storing accordingly. Now, having a great system is fantastic, but it's only effective if you actually maintain it. So let's turn these big principles into a simple checklist you can use to make safety a daily habit. Let's start with the containers themselves. Think of this as like a quick annual checkup. Are the caps on tight? Can you actually read the label clearly? Do you see any cracks or maybe some weird crystals forming on the outside? And are the lids themselves in good shape? Because a failing container is basically just a spill that hasn't happened yet. And where you actually put your shelves and cabinets matters a ton. First off, don't store chemicals, especially the heavy ones, above eye level. That's just asking for trouble. Keep them away from sinks, heat sources, and electrical outlets. And some places are just absolute no-go zones. The floor is a trip hazard, fume hoods need to be kept clear for airflow, and exit aisles must always be kept clear. No exceptions. When it comes to labeling, the absolute key is consistency. Every single container, whether it's permanent or just temporary, needs a label with its name and its primary hazard. That beaker of solution you just made for an experiment, label it. That squirt bottle of diluted cleaner you're using for the afternoon, label it. An unlabeled container is a complete mystery. And you know what? Mysteries are dangerous in a lab. Here's a simple but really powerful idea. Less is more. Honestly, the best way to reduce the risk from hazardous chemicals is to just have less of them. By only keeping about a 1 to 2 year supply, you cut down on clutter, you minimize the risk of accidents, and you avoid that whole problem of old expired chemicals that we saw earlier. And finally, a rule that is absolutely non-negotiable. 0. That is the number of food or drink items that belong in a refrigerator that is used for storing chemicals, samples, or any lab materials. There are no exceptions to this. Cross-contamination is a serious, serious risk, and the separation has to be total. So we've gone from chaos to control, from the big principles to daily practices. Now, I'm going to leave you with this one question to think about. Looking at your own lab, your own classroom, what's the very first safety change you're going to make? Thanks for joining me.